Thank you for joining us today as we delve into the critical role of a network security engineer. As digital infrastructures expand and cyber threats evolve, this role has become essential in protecting organizational assets and ensuring secure communication across networks. In this session, we explore the practical challenges, core responsibilities, and technical expectations that come with the position. From firewalls to threat detection, encryption protocols to vulnerability assessments, the network security engineer stands at the front line of digital defense. Let's now dive into a detailed interview format to uncover the depth of expertise required in this vital IT security role. 1. What are the primary responsibilities of a network security engineer within a modern enterprise environment? A network security engineer is primarily responsible for designing, implementing, managing, and upgrading security measures that protect an organization's computer networks and systems. In a modern enterprise setting, this encompasses a broad scope that ranges from establishing firewalls and intrusion detection systems, IDS, to ensuring secure remote access and configuring network segmentation. These professionals are often tasked with creating security protocols, setting up virtual private networks, VPNs, and coordinating with other IT teams to ensure integrated security efforts. Furthermore, a network security engineer regularly conducts vulnerability assessments, audits security systems for compliance, and monitors network traffic for unusual or unauthorized activity. Their role also includes documenting security breaches, coordinating response actions, and analyzing the aftermath to prevent future incidents. They need to maintain up-to-date knowledge on emerging threats and apply patches and updates to software and hardware as needed. In a landscape that is continuously evolving due to the proliferation of mobile devices, cloud computing, and Internet of Things, IoT, technology, network security engineers are required to adapt defenses rapidly and proactively. The position is also increasingly involved in strategic decision-making, especially around designing secure network architectures and enforcing company-wide security policies. 2. How do you approach risk assessment and vulnerability management in enterprise networks? Risk assessment and vulnerability management are foundational tasks for network security engineers and require a systematic approach to be effective. The process typically begins with asset identification and classification, where the engineer determines which systems, data, and services are most critical to business operations. Once assets are prioritized, vulnerability scans are conducted using tools like Nessus, Qualys, or OpenVAS to detect known security weaknesses. These findings are then analyzed in the context of threat intelligence feeds and organizational risk appetite to assess potential impact. An effective approach involves categorizing vulnerabilities by severity, critical, high, medium, or low, and creating mitigation strategies tailored to each risk level. High-priority threats may necessitate immediate patching, firewall reconfiguration, or temporary shutdowns, while lower-risk items can be scheduled for routine maintenance. It's crucial to include zero-day vulnerabilities and advanced persistent threats, APTs, in the risk model, even when no immediate fix is available, by applying compensating controls or segmentation techniques. Risk assessment must be a continuous loop rather than a one-time activity. Engineers often deploy automated tools for regular scans, combine them with manual penetration testing, and keep audit trails for future reviews. They also communicate findings clearly with stakeholders and recommend security best practices. In enterprise environments, aligning vulnerability management with compliance frameworks such as ISO 27001 or NIST is important. 3. What methods do you use to detect and respond to intrusion attempts or anomalous network behavior? Detecting and responding to intrusion attempts or anomalous network behavior involves a layered defense strategy supported by real-time monitoring and advanced analytics. Network security engineers typically deploy intrusion detection systems, IDS, and intrusion prevention systems, IPS, such as Snort, Suricata, or Cisco Firepower, to monitor traffic for known signatures or behavioral anomalies. These systems can alert administrators or automatically block suspicious activities based on pre-configured rules. Engineers also rely on security information and event management, SIEM, tools like Splunk, ArcSight, or QRadar to aggregate logs and analyze patterns across multiple endpoints and servers. Machine learning algorithms are increasingly employed to detect subtle deviations from normal activity, such as unexpected data flows or login attempts at unusual hours. Behavioral analytics may highlight lateral movement, privilege escalation, or data exfiltration attempts that traditional tools might miss. Once an intrusion attempt is detected, a swift incident response protocol is essential. This typically includes isolating the affected systems, preserving forensic data, and performing root cause analysis. Engineers must then patch the vulnerability, remove malicious code, and restore systems from known good backups. 4. Can you explain the role of firewalls and how you configure them for optimal network security? Firewalls play a central role in network security by acting as the gatekeepers between internal networks and external entities. They control incoming and outgoing traffic based on predetermined security rules and are essential for enforcing access control policies. Network security engineers configure firewalls to restrict traffic by IP address, port number, protocol, or application-level criteria, thereby minimizing the attack surface. Modern enterprise environments utilize both traditional hardware firewalls and next-generation firewalls, NGFWS, like Palo Alto, Fortinet, or Checkpoint, which include features such as deep packet inspection, intrusion prevention, and application awareness. When configuring a firewall, engineers follow the principle of least privilege, only allowing traffic that is explicitly permitted. Default deny policies ensure any undefined traffic is automatically blocked. Network segmentation is also implemented through firewalls to isolate sensitive zones like finance, HR, or RD from the broader network, reducing the risk of lateral movement in the event of a breach. Rule optimization is crucial to maintain performance and prevent configuration drift. Engineers periodically audit firewall rules, remove redundancies, and log denied connections for threat analysis. They also implement NAT, network address translation, rules to mask internal IPS and support secure remote access via VPNs. Firewall configurations are tested rigorously using penetration testing and validated against regulatory requirements. 5. What is the importance of encryption in network security, and how do you implement it? Encryption is vital in network security as it ensures the confidentiality and integrity of data in transit and at rest. By converting readable data into ciphertext, encryption prevents unauthorized access even if the data is intercepted. Network security engineers employ encryption to secure communication channels, protect sensitive information, and comply with data protection regulations. Transport layer security, TLS, is widely used to encrypt data transmitted over the Internet, especially in HTTPS connections, email protocols, and virtual private networks. Engineers configure SSL/TLS certificates on web servers, mail servers, and APIs to enable encrypted sessions and prevent man-in-the-middle attacks. For internal communications, IPsec protocols can secure traffic between network devices or branch offices. Encryption also applies to storage solutions where data is encrypted using standards like AES 256, often implemented in database management systems and endpoint devices. Engineers manage encryption keys through centralized key management systems, KMS, ensuring access control, rotation policies, and secure storage. Public key infrastructure, PKI, is used to manage digital certificates and facilitate secure authentication. Additionally, full disk encryption on laptops and mobile devices protects against data loss in case of theft. Implementation involves selecting appropriate algorithms, ensuring compliance with standards like FIPS 140-2, and avoiding weak cipher suites. 6. How do you ensure secure remote access for employees and third-party vendors? Secure remote access is essential for modern work environments, especially with the rise of remote work and outsourced services. Network security engineers implement virtual private networks, VPNs, to provide encrypted tunnels between user devices and corporate networks. Solutions like Cisco AnyConnect, OpenVPN, or Fortinet VPN ensure that data transmitted over public networks remains confidential. Engineers configure multi-factor authentication, MFA, to add an extra layer of identity verification, significantly reducing the risk of credential theft. Role-based access control, RBAC, ensures that users and third-party vendors only access resources necessary for their tasks. Network segmentation further limits access by placing remote users in restricted zones or virtual LANs. Engineers also implement endpoint security checks using network access control, NAC, solutions to ensure devices meet security posture requirements before granting access. For third-party vendors, access is often time-bound and monitored through dedicated secure portals or jump servers, ensuring traceability and reducing exposure. Session logging and real-time monitoring help detect unusual behavior or policy violations. Engineers frequently review access logs and conduct audits to ensure compliance and minimize the risk of unauthorized access. In cloud environments, secure remote access is managed through Identity and Access Management, IAM, systems that enforce least privilege principles and track user actions. Training users on phishing and secure connection practices also forms part of the access strategy. Together, these measures create a robust framework for secure, efficient, and controlled remote access across the enterprise. 7. Describe your experience with Security Information and Event Management, SIEM systems. Security Information and Event Management, SIEM, systems are critical tools for real-time security monitoring, log management, and threat detection. Network security engineers use SIEM platforms like Splunk, IBM QRadar, Logarithm, or ArcSight to collect, normalize, and analyze data from diverse sources including firewalls, servers, endpoints, and applications. The core purpose is to identify potential security incidents by correlating events and highlighting anomalies that warrant investigation. Engineers are responsible for setting up data feeds, defining correlation rules, and tuning alert thresholds to reduce false positives. Custom dashboards and automated alerts enable timely responses to suspicious activity such as brute force attempts, privilege escalations, or lateral movements. SIEMs also support compliance by generating reports for regulatory standards like HIPAA, PCIDSS, and SOX. Engineers use them to conduct forensic analysis, trace incident timelines, and determine the scope of breaches. Integration with threat intelligence platforms enhances detection by comparing logs against known indicators of compromise, IOCs. Experience with SIEM includes scripting for custom parsing, maintaining storage for log retention, and optimizing performance in large-scale deployments. 8. How do you stay updated with emerging cybersecurity threats and evolving technologies? Staying updated with emerging cybersecurity threats is vital in an ever-changing threat landscape. Network security engineers adopt a multifaceted approach that includes subscribing to threat intelligence feeds from sources like AlienVault OTX, Cisco Talos, and the USCERT. Following cybersecurity blogs, vendor advisories, and communities like Reddit's NetSEC or Stack Exchange helps engineers keep tabs on recent vulnerabilities, zero-day exploits, and mitigation techniques. Participation in webinars, industry conferences, and online training platforms like SANS, Offensive Security, or ISC Superscript 2 provides deep dives into advanced topics and real-world attack scenarios. Engineers often engage in Capture the Flag, CTF, competitions or virtual labs on platforms like Hack the Box or TryHackMe to sharpen hands-on skills. Subscribing to CVE databases and our SS feeds for software updates ensures they are aware of patch releases. Membership in professional bodies like ISACA or ISC. Superscript 2 offers access to white papers, policy updates, and certification resources. Engineers also use social media channels, GitHub repositories, and security podcasts to stay in the loop. Regular collaboration with colleagues and threat hunters within their organization facilitates knowledge exchange and fosters a proactive culture. Additionally, they schedule time for research and integrate learning into their daily workflow. In a field where yesterday's defense may not stop today's attack, ongoing education is not optional. It's essential. 9. How do you respond to and recover from a data breach incident? Responding to a data breach requires immediate, structured action to minimize impact and restore security. The process begins with identification, using SIEM alerts, logs, or user reports to detect unauthorized access. Network security engineers swiftly isolate affected systems to prevent further spread and preserve forensic evidence. Containment is followed by eradication, where malicious files are removed, vulnerabilities patched, and compromised credentials revoked. The recovery phase includes restoring systems from clean backups and verifying integrity through testing. Engineers coordinate with internal stakeholders, including legal and communications teams, to manage disclosure obligations. Post-incident, they perform root cause analysis to understand how the breach occurred and what controls failed. This leads to policy updates, revised firewall rules, or upgraded authentication mechanisms. Documentation is created to inform compliance reports and guide future responses. Communication with external partners, such as incident response vendors or forensic investigators, may also be necessary. Engineers update monitoring tools to detect similar attempts in the future and ensure that lessons learned are shared across departments. 10. What security certifications do you hold, and how have they enhanced your capabilities? Security certifications validate expertise and provide structured knowledge in the cybersecurity domain. Network security engineers often pursue certifications such as CompTIA Security Plus, Certified Ethical Hacker, CEH, Cisco Certified CyberOps Associate, and more advanced credentials like CISSP, CISM, or CCNP Security. These programs cover essential topics such as network defense, encryption, access control, and secure design. Certification exams test both theoretical knowledge and practical scenarios, which help engineers apply best practices in real-world settings. For instance, earning the CISSP enhances understanding of governance, risk management, and architecture, while the CEH focuses on offensive strategies to think like an attacker. Vendors like Cisco and Palo Alto also offer product-specific certifications that enable engineers to deploy and configure their technologies effectively. Certifications often require continuing education, ensuring that engineers remain current on threats and innovations. They also boost credibility with employers and clients, demonstrating a commitment to professional development. Beyond technical skills, certifications build critical thinking, documentation habits, and policy understanding that are crucial in complex enterprise environments. The role of a network security engineer is crucial in defending against evolving cyber threats. With a deep understanding of security tools, protocols, and risk management, these professionals ensure organizational resilience and data integrity across complex digital environments.